So today we are going to discuss about the properties of Z transform. So as similar to that of Laplace transform, here also we have first one is linearity, and secondly we have time shifting, and third one we have time scaling, fourth one time reversal, and fifth one we have scaling of Z, and then sixth one is conjugation, and seventh one we have accumulation, and eighth one is convolution, and ninth one multiplication, tenth one differentiation, and 11th one differentiation in Z domain, 12th one initial value theorem, and 13th one we have a final value theorem. So as similar to that of Laplace transforms, here also we have initial value and final value theorem. In the initial value, we are going to apply limit z tends to infinity, whereas in uh, Laplace transforms, so we applied s tends to infinity. In the final value, we are going to apply s as 0, and here s as here z as 0. And that is these are the two as similar, except s and z remaining all the things are same. So let's have a quick look on these properties of z transformation. As we know, the linearity property they discuss as, if I'm having my sequence as x1 of n, and my second sequence I have x2 of n. Okay, if I'm applying z transformation to this, I can get this as x1 of z, and here I will get as x2 of z. So if I'm going to add these two signals by multiplying a constant like a with respect to x1 of n, and b with x2 of n, if I'm applying z transformation to this, once again I can get this as a into x1 of z plus b into x2 of z. So this is the thing present in the linearity property. This is the thing present in the linearity property. And then next one we have time shifting property. Next one is the time shifting property. In the time shifting property, if I'm having my sequence as x of n, if I'm applying z transformation, I can get this as x of z. And if I'm having a delay, a positive delay by n naught, a positive delay by n naught, my sequence will be, after applying z transformation, that can be written as z power minus n naught into x of z, So if you require any proof for this, please go through my notes. I will forward the notes after completion of this particular module. uh, so priorly I'm not sending, don't mind, because after sending this thing also, after before examinations, once again you people are going to ask. So that's why I'm waiting. So after completion of these modules, definitely I will forward our entire things. Okay. So next one is a time scaling property. This is a time shifting. This is time shifting. And then we have time scaling. What is meant by scaling? In the what happens in the shifting? What happens in the scaling? Shifting means we are going to perform only two operations, that are addition and subtraction of any value with the prescribed location n. So here shifting has been done by n naught. It is subtraction. In subtraction means it is a positive side. It is a right shift. It is a right shift. If it is a here n plus n naught means it is a left shift. It will move to the negative side. So we already discussed related to that. So next one, coming to the scaling. Time scaling means I'm going to multiply or divide my sequence length like this. I'm going to multiply or divide my sequence here. So for example, here I have multiplied. For example, I am having my sequence x of n, and I can get this as x of z. Whenever I'm going to perform a time scaling by an, a is multiplied with the n, then my z transformation can be written as x of z power minus a, x of z power minus a. Okay. Now, if I'm going to have, this is multiplication case. If I'm having division case, like x of a divided by, sorry, n divided by a, if my value is n divided by a, if that is the case, I'm going to have my signal as a transformed signal as x of z power a plus a we are going to have. Plus a we are going to, okay. So to this, go through, yeah, that is very simple proof. If you are going to apply that particular Z transformation basic kernel, we can identify this. What is a Z transformation basic kernel? X of Z is equals to summation n is equals to minus infinity to plus infinity x of n e power, sorry, z power minus n. So in this, we need to substitute that. Automatically, we are going to get the solution. So next one is time reversal. Next property is time reversal. So what is meant by time reversal? If it is a positive right-handed signal, that will be converted into left-handed signal. If my right-handed signal is there, that will be converted into left-handed signal. Then we are going to call that as a folded signal or time reversal signal. So if my signal is plotted like this, then this is a shifted or time reversal version of this particular signal. We can call this as, okay. So this is a time reversal version. So in a Z transformations also, if you are going to have like, I have my signal as x of n. If I'm going to apply Z transformation to this, I can get this as x of z. And if I'm having my signal as x of minus n, and then in that case, my Z transformation is can be written as x of z inverse, x of z inverse. Okay. Now, the next property is, so far, what we discussed. So far, linearity, time shifting, time scaling, and time reversal we discussed. Now, the fifth property is scaling of z. How we are going to scale the z? So the z is scaled as scaling. So if I'm going to take this, I can write this as x of n. X of n, if I'm applying z transformation to this, I can get as x of z. I'm getting inverse z transformation, I can get x of n IZT, and here I can write as zt. So here, if I'm having it multiplied with a power n into x power x of n sequence, then I will have my z transformation as x of z divided by a. Z divided by a. This is the thing we are going to have. Okay, this is a scaling property. Scaling of z. Previously we have time scaling, but this is z scaling. Z means z domain axis. Z domain axis ni scaling chase. How I am going to perform the scaling in the z domain. This is a division. If you are going to have a power minus n means you will have a into z. Okay, so that is different. Okay, so this is the thing. Next we have our another property is conjugation. Another property we have is conjugation. So what is meant by conjugation? Conjugation is if I'm having my sequence as x star of n, I will find my z transform of this particular sequence as x star of z star. X star of z star. Okay, this is the conjugation. Already you people know about the complex conjugation. What happens in the complex conjugation? If I'm having a plus ib, that will be created as a minus ib. That will be taken as a minus ib. So similarly here also in the z transformation also, we are going, if we are having x of n as a sequence, I'm going to find my result as x star and z star. X star of z star. Okay, so this is the thing about conjugation. The next one we have is accumulation. So what is meant by accumulation? Why we are calling this as accumulation? Previously we didn't read about this particular accumulation named any property. Yes, we didn't read it, but we know that. So what is that? Integration. We know about integration in time. So integration in time, whenever we are going to perform integration, means that signal or that function is a continuous signal. So if it is not a continuous signal, what we are going to do is we are going to perform the summation. We are going to perform the summation. In other words, we can call that as a accumulation also. So if I'm having my signal x of n, if I'm having my sequence as x of n, it will be converted as x of z after applying z transformation. Now let us consider I'm replacing my n with the k. If I'm replacing n with the k, and the length of the sequence I'm representing as 1 to n. Okay, ఇప్పుడు అర్థమైందా? Why I am taking as a k? Because the length should be represented with 1 to n, because as we are learning from basics, not only in this subject, in the mathematics, we are going to represent with the n. So I'm going to replace this particular n with the k here. So with that I can represent the length. Okay, so this can be written as summation k is equals to infinity to n x of k. If you are applying z transformation to this, if you are applying z transformation to this, I can find the solution as x of z divided by 1 minus z inverse. 1 minus z inverse. So if you require proof means go with the notes. Okay, I don't want to repeat once again. If you require any proof means please go through the notes, and if you have any doubt after that also, please let come to me at any point of time. No need to no problem at all. Okay. The next property we have is convolution. So what is meant by convolution? So multiplication of two sequences, one after two sequences, yeah, subspaces each and every point. Means if I'm having my sequence x1 of n with the length of, for example, it is having a three variable that is called as a, b, c. Let us know. Let us consider. So if I'm having another sequence x2 of n, x2 of n, it is also consisting of three variables. Let us consider d, e, and f. Now what the convolution says is the length of the length of this, how much length of this and how much length of this is there, the total number of variables will be this plus this minus 1. After performing the convolution, x1 of n is convolved with x2 of n. So the length will be, so you are going to have like I, j, k, l, and m. These are the values you are going to have. What is I? I indicates the a into f. Okay. Next, what is j indicates? J indicates the b into f plus a into e. Okay. Next, what the k indicates? K indicates that, so c will be multiplied with the f, b will be multiplied with the e, and a will be multiplied with the d. That is the k. What is the, what about the l? L will be, L will be, so c will be multiplied with the e and b will be multiplied with the d. And finally m. What is m? C will be multiplied with the d. That is only the last part we are going to have. So I will write once again the equations here, with that you can understand what is convolution in discrete case. So what is I? I is equals to a into f. A will be multiplied with the f. After that, j. What is j? J is equals to a into e plus b into f. B into f. B into f. Next, whereas coming to the k, I'm going to have as a into d plus b into e plus c into f. What about the L now? L is equals to b into d plus c into e. M, what is M here? M is equals to C into D. Totally 5 values we are going to have. If you remember the graphical representation, graphical execution of convolution process, there you can see the same operations over there. So from this, I can write my equation. I can write my equation as uh, summation n is equals to, or k is equals to 1 to m plus n minus 1. M indicates the length of x1 of n, x2 indicates the length of this, and so here I can write as x1 of n into x2 of m minus k. So x1 of k, x2 of m minus k. So like this, if you are going to perform the multiplication, I am able to get this sort of results. So finally, if I am going to perform the convolution in z domain, if I'm going to perform, so this is equal to, as similar to that of Laplace transforms and Fourier transforms, it can be written as x1 of z is multiplied with x2 of z. So convolution, instead of doing convolution, if I am going to transfer them into the z transform, after multiplying, whatever the result I am going to get, that result is equivalent to the x1 of n is convolved with the x2 of n. Okay, this is the thing we are going to have. The next property we have is multiplication. So what is meant by multiplication in general? So the multiplication is x1 of n and x2 of n dot product. If I am going to perform a dot product, this is equals to the, in z domain I can write this as 1 divided by 2 pi j x1 of z is convolved with x2 of z. So you can see some change in the previous one to this one. You can identify some change present in the previous one to this one. If you are doing in a discrete case, in the plain discrete case, n domain, convolution means simple dot multiplication in a z domain. Whereas coming to in n domain, if you are going to have a dot product or simple multiplication, whereas coming to in z domain, that will be convolution. We already know about this particular thing in the previous lectures and all. And the last one, in the last next one is differentiation. The next property is differentiation. The differentiation in n domain or basic discrete signal domain means d by dn of x of n is equals to, which is nothing but the difference between a previous sample to present sample, right? So I can write this as x of n minus x of n minus 1, x of n minus 1 with respect to the time n minus 1, n minus of n minus 1, which is equals to x of n minus x of n minus 1, because n minus n plus 1, so nn gets cancelled. So I will write this as x of n minus x of n minus 1. So I will write one more step here. So nn gets cancelled here, and I can get this as x of n minus x of n minus 1, x of n minus 1. So the differentiation, basic differentiation, what happens with respect to n? It is going to calculate the difference from previous sample to present sample. That's it. So this is a discrete case. If I am applying z transformation to this, what happens? The z transformation will be, if I am applying z transformation to this, I can get the result as z minus 1 divided by z into x of z I am going to get. Because here I have two sequences. One is x of n and another one is x of n minus 1. So if I'm doing x of n minus 1 Laplace z transformation to that, I can get 1 minus z inverse into x of z, which is nothing but z minus 1 divided by z into x of z. Okay. So this is differentiation in plane signals, in discrete signals. If I'm doing differentiation in z domain, if I'm doing differentiation in z domain, x of n is my signal sequence. If I'm applying z transformations to that, I will get as a x of z. And if I'm differentiating z x of z with respect to z, I am able to get the value as n into x of n into x of n. How we are going to get? So d by dz x of z. So I will have minus z also. So how we are going to have? So let's, I want to have proof. I want to explain proof for this particular thing. So let's see the proof only for this. Remaining things I don't want to. This will become completed in 2 to 3 minutes, not more than that. So in general, what is x of z? X of z is equals to summation n is equals to minus infinity to plus infinity x of n, x of n into z bar minus n. Now, if I am differentiating this particular x of z with respect to z, what happens? X of z, and in the x of n, I don't have any z terms, so directly the summation will be remains the same, but but the differentiation moves to z power minus n. So it can be written as dz divide differentiation of z power minus n. So what is the differentiation of z power minus n? Minus n into z power minus n minus 1, minus of n minus 1. So I can write this as summation n is equals to minus infinity to plus infinity x of n. So after differentiating z power minus n, I can get this as minus n into z power minus n minus 1, minus n minus 1. So from this, I can write this as once again, so summation n is equals to minus infinity to plus infinity n into x of n minus, I will bring here, and this can be, it can be written as z power minus n and into z power minus 1. So this z power minus 1 I'm going to send to this side, and z all negative sign also, if I'm going to send it to this side, LHS side, I can write this as, I can write this as, so minus z the differentiation of x of z is equals to n into x of n, n into x of, it's a z transform, inverse z transform, if you are aware. Okay, so this is the result we are going to have. Okay, this is about the differentiation property. Next we have our next property is initial value theorem. So in the initial value theorem, x of n, if I'm having my sequence, I will get my z transformation as x of z, x of z. Now if I'm going to substitute my n value is equals to 0, I can get my signal x of 0. So this can be written as a limit z tends to infinity, the limit z tends to infinity x of z, limit z tends to infinity x of z. So how we are going to get this particular solution? Please follow the steps of Laplace transform. There you can see that. Okay. Similarly, in the initial, this is the initial value theorem. Whereas coming to the final value theorem, the final value theorem, I have my signal sequence as x of n, my sequence as x of n, and I have, I will get this as x of z if we am applying z transformation to that. Now, if I am going to substitute x of infinity, with that I can get the final value. But in the z domain, if I am going to apply z tends to 0, z tends to 0, I can get this particular final value theorem. But final value. So, but the thing is, here we are not going to apply 0. We are going to apply z is equals to 1. Z is equals to 1, because as z power minus n, if I am having my z value as 0, it is power in the negative. If I am having 1 means, once again it will come to the denominator, but something divided by 0 means it will move to infinity. So our ultimate intention is not to get infinity values, right? So that's why we are going to place z is equals to 1, and here we have x of z, x of z, this will be multiplied with the 1 minus z inverse. So why we are going to multiply with the 1 minus z inverse? So to compensate that z is equals to 1, compensate that z is equals to 1, we are going to multiply with the 1 minus z inverse. Okay, these are the basic properties of z transformation. These are the properties of z transformation. So the important concept that is related to the region of convergence, or region of convergence. What is meant by ROC, region of convergence? So the what is meant by region of convergence here? The region of convergence, it can be it is where, at what limits my z transform getting exist, my z transformation is getting exist, such things we are going to call as the region of convergence. So here we have some properties of region of convergence, and let's have a quick look on this particular properties of a region of convergence, or ROC. We can write simple words as ROC. The first point is the ROC is a ring in Z transformation. The ROC is a ring, means it is in circle size. It is circle. Okay, a ring or a disc in the Z plane. Z plane centered at origin. Centered at origin. The next property we have is, I will finish off very quickly. The time is not much. The ROC is if the ROC is a finite duration, is a finite duration and causal, then the ROC is, then the ROC is entire Z plane except, entire Z plane except except z is equals to 0, except at z is equals to 0. Next one, the ROC cannot contain any poles. The ROC cannot contain any poles in Z transformation. Okay, the fourth point, if my x of n is finite duration, is allowed at finite duration and anti-causal, then the ROC is entire Z plane except, entire Z plane except at Z is equals to infinity. Except Z is equals to infinity. Okay. If it is a double-sided, if x of n is finite duration, x of n is finite, is allowed for finite duration, and it is a two-sided signal, two-sided sequence, then the ROC is entire Z plane two-sided sequence, then the ROC is entire Z plane except except z is equals to 0 and z is equals to infinity is equals to infinity. So the ROC must connected to ROC is must connected to origin, must connected to origin. And the last one we have is the ROC of LTI stable system contains unit circle. The ROC of an LTI stable system contains unit circle. So these are the various properties of a region of convergence related to this particular Z transform. And I require one more class to complete this particular problems and all. And along this thing, we need to have one more session. Two more sessions are required for me to explain about the inverse Z transformation, which is very important in a practical realizations perspective, along with the Laplace transforms. In the discrete case, they are going to utilize this particular Z transformation. Okay. So see in the next class I will explain you what is inverse Z transformation and some of the problems related to this particular thing. Okay. If you have any queries, please let me know in WhatsApp or something else, whichever the medium you are convenient. Okay. So thank you. Have a nice day, and one more session we will meet. Huh? So next session we will have problem session. How to solve the Z transformation based sequences. Okay. Thank you. Thank you all.